G'day, in this video we're going to build on a concept of electricity and focus on the concept of electrical energy and its transformation to different types of energies. This video covers dot point 4.2.3, we're looking at electricity and magnetism. Inquiry question 2, focus on the process of transfer and transformation of energy in an electric circuit. And in particular, we're looking at this transformation of energy as we move from electrical potential energy to whatever the electrical component is converting energy into. Particular focus is going to be placed on this video to introduce this new equation here, P equals VI. Our key learning intentions for today is to first define electrical power and relate electrical power to the variables current and voltage. Do a quick review of energy transformations, particularly when focusing on electrical components, and then complete a couple of simple calculations which apply Ohm's law as well as our new concepts around electrical power. So first off, electrical power, P, is the amount of energy that an electrical component can convert over a period of time. So our core power equation, P equals VI, shows up in our datasheet in the electricity and magnetism section. But this isn't the first time that we've seen power, which effectively is the measurement of how many joules of energy are being released or used per second. This version of our power equation was seen in Module 2. During this module, we learnt that power was measured in watts, capital W, or could also be written as joules per second. In our electricity and magnetism version of the equation, P equals VI, generally we still consider power to be measured in watts, joules per second. However, we see that power is related by voltage and current. It's the product of the voltage and the current. And I'm actually going to use two equations that we've used previously to show you how we come up with this equation to begin with. We can do this by using one equation for voltage, delta U on Q, and one equation for current, which is I is equal to Q on T. So we know that V is equal to delta U on Q. Similarly, we could also talk about voltage as a generic change in energy over the charge. And for current, we know that it is the amount of charge which passes a point every second. If we were to multiply voltage and current together, this could mean that we could sub in the right-hand side of both expressions. So VI would be the same as delta E, the change in energy, over Q, multiplied by Q on T. What that leaves us with, if we cancel out our Q's, is that VI is equal to delta E, the change in energy over time. This looks quite familiar. This is directly linked to our original power equation, meaning that V times I is essentially the change of energy over time, meaning that if we do multiply voltage by current, it will give us the power of the component, the amount of energy it's able to convert over a period of time. Therefore, we don't just need to write that VI is equal to delta E on T, but then we can also say that power is equal to VI as well. Generally speaking, we measure power in watts. It could also be quoted as joules per second. And given that we can calculate power by multiplying voltage and current together, technically, power can also be measured as voltamps. When looking at various electrical equipment or components, these technologies are generally given some sort of wattage rating. And what this wattage indicates is how much energy is being consumed per second. In other words, how much electrical potential energy is being converted into other forms of energy. So, for example, if we were to look at our light globes, the watt values that we are being shown here indicate a certain amount of electrical potential energy is converted into heat and light energy over a set period of time. Similarly, on the bottom of the kettle, the tag indicates the rough amount of energy which is being converted from electrical potential to heat energy every second. Something that I do want to note here though is if we look at some of these different light globes, we should notice here that different wattage ratings for these light globes result in the same brightness or emission of light. So for example, a standard light globe will emit 450 lumens worth of light by converting 40 joules of energy per second. However, an LED globe is able to achieve the same brightness by only converting 6 joules of energy per second. What this inherently means is that there is a difference in efficiency. So something that we're going to discuss in class, but I want you to reflect on for the moment, is why there are differences in efficiency. An answer which I want you to try and get to yourself, and again, we'll discuss in class. To round off this video, what I want to do is go through a couple of quick calculations just to apply the P equals VI concept. There'll also be a slightly more complex problem to follow, which requires the use of a few different formulae. This first question, though, is quite simple. It says to calculate the current which flows through an 800 lumen CFL globe, assuming that the globe is powered by a 240 volt main supply. This question only requires the use of one equation. However, we will need to extract some key information from the data that's been provided on this slide. So if we're using an 800 lumen CFL globe, what that will mean is that the globe is rated at 14 watts. This value is our power. In the question, we've also been told the voltage of the power supply, which will give the light globe energy, and that is 240 volt mains. And we're being asked to calculate the current I. That's something that is not known. Now, because we have P, V, and I makes our solution pretty easy, we're going to use the equation P is equal to V times I and rearrange to make I the subject. That will give us P on V as a way to calculate it. All we need to do is substitute to solve. It should give us an answer of 0.058 amps to two significant figures. In this second question, we're looking at a resistor which is rated at 11.5 ohms, and it's powered by a transformer which supplies 6.7 volt, and we're being asked to calculate the amount of energy converted into other forms if the circuit was turned on for 10 seconds. So in this question, we've been given two values. We've been given resistance, which is 11.5 ohms. We've been given the voltage of the power supply, which is 6.7 volt. And we're being asked to calculate E, the amount of energy that's being converted over 10 seconds. Now, in order to calculate for E, we're going to actually need to use three separate equations. And in order to show you the solution, I'm going to work backwards. So when I look at this question and I see all of these electrical measurements, and I know that we're being asked to calculate for a raw energy value, something that's measured in joules, the first thing that I think about is the idea that somehow, somewhere, we need to be calculating for power. And what that probably means is that we need to use P is equal to VI. We're partway there. We should be able to calculate for power because we already have voltage. We will need current though, and I'll get back to how we can calculate that in a second. Once we have power, knowing that we already have one variable and it's very likely that we'll be able to find the other, we also know by a module 2 equation that power is also equal to delta E. So in other words, the amount of energy which is being used or consumed divided by our period of time. Assuming that we can calculate power, and given that we know how long the circuit's been turned on for, that T is equal to 10 seconds. So far it's looking like I'm coming up with a pretty good strategy to come up with a solution. The only issue is that we do not have current. However, trusty Ohm's law will help us in this regard. We know that V is equal to I R. And considering that we already have voltage and resistance as known values, calculating for I is quite straightforward and simple. And this is what we're going to do first. So in order to do that, I'm going to make I my subject and then substitute and solve. Now that I know my current, I'm going to calculate for power. And now that my power is known, I can rearrange my power equation from module 2 to calculate for the energy change. And in the end, to two significant figures, my answer should be 39 joules. Thank you very much, everyone. In the next video, we're going to build on our understanding of series and parallel circuits. We should already be pretty familiar with how they're constructed and maybe even have some ideas about how energy of series and parallel circuits can be different. What we will be focusing on, though, is building on our understanding of quantitative concepts and relationships for components which are arranged in series or parallel. But until then, have a good one.